Welcome students. The next video in this quarantine content lineup is compact sets in real numbers. This will be a series of lectures on this topic. So today we'll be talking about the definition of a compact set and the Heine Borel theorem. So let's start. So compact sets are hugely important in analysis. They are natural generalization of finite sets. Holding hands with continuity, this property makes our lives way much easier to deal with. In this lecture, we'll be learning the most general definition of compactness and a few criteria that when a set of real numbers becomes compact. So let's start. So let's get the motivation first. Let us start with the literal meaning of the word compact. Now, Google says it means closely and neatly packed together, dense. Let us see two subsets of R, which one of that agrees to this meaning, closely and neatly packed together. One is 0 to infinity, starting from 0 going till infinity, and the other one is closed interval 0, 1. So, which one of these would you want to call a compact set? Obviously, the second one. The first one is too large to handle with, isn't it? So, mathematically speaking, we want a compact set to be bounded. Okay. Now, let us consider these two following subsets: 0, 1 closed interval and 0, 1 open interval. Both are bounded. We agreed in the last slide that we want our compact sets to be bounded. Now, here both are bounded. Which one will you want to call as a compact set? Confused? Okay, let's see these two following pictures. Now, these two are birthday gifts. Both are birthday gifts, both are beautiful, but which one do you want to call a compact packaging? Okay, so of course the second one. The first one leaves too many loose ends untied, just like the open interval 0, 1. Which leaves both of its ends 0 and 1 untied, not included there. So we sort of agree to call the closed interval 0, 1 as an example of a compact set. So we, in other words, we agree to call a compact set to be a closed set as well. Okay. So far, by the literal meaning of the word compact, we have agreed to call a closed and bounded subset of real numbers as a compact set, which is obviously a very nice and good definition, which is an equivalent definition in the case of real numbers. Alright? But compact sets go a way longer way than the mere set of all real numbers. So we need to define a robust and more general definition of compact sets which can be used everywhere. And we must not forget that of course that new definition must be in line with our intuition, that is a compact set should be closed and bounded about compact sets in R. So the new definition must fall in line with closed and bounded subsets to be compact in the set of real numbers. Okay, so for that purpose, we introduce a new concept which is called the open cover. Let's see. So first understand what is cover. Suppose you are in a football manufacturing unit of a company, say Adidas, Nike or whatever, and holding a football bladder, the rubber ball inside the football what you play with. Your job is to cover that bladder with hexagonal leather patches to make it playable. Okay. Now, as you are in a manufacturing unit, for the sake of analogy, it will not be unjustified to assume that you have infinitely many of those leather patches available. Okay. Of course, all the patches can cover the one bladder you are holding, but you definitely do not need all of them for your job, isn't it? So you choose only say 32 patches to cover up the entire wall. Okay. Now the collection of all leather patches in the company is a cover of the bladder you are holding. Okay, all of them together can cover the entire bladder, of course. And the collection of those finitely many patches, the 32 you chosen, finitely many patches you chose to actually cover the bladder is called a finite subcover of that cover. Alright, so this is what is called an cover and subcover in the general setup, in the general meaning. Now let us apply this thing to mathematical precision. Okay, so we start with an arbitrary set A. Mathematically, a collection G, script G, which has the set G lambda, where capital lambda is an index set. G lambda, the small lambdas are coming from the index set capital lambda. That is called a cover of A if A is covered by all of G lambdas. That means the union of all the G lambdas where the small lambda is varying over the index set capital lambda. This union will be a superset of A. Then this collection script G is called a cover of A. Fine. Now what is a subcover, finite subcover then? In general, the index at capital lambda can be uncountably as well, uncountably infinite. If you can find finitely many G lambdas to cover your entire A, just like the example in the football company, you had infinitely many leather patches available to you, but you do not need all of them to cover the bladder you are holding. So you need only finitely many. So if you can find finitely many G lambdas from this collection G lambda over here, from this collection, then that is, if you can find the set G lambda 1, G lambda 2, G lambda 3 up to G lambda n such that A is a subset of the union of all of them, then these collection G lambda 1, G lambda 2, G lambda 3 up to G lambda n, these collection of open sets will be called a finite subcover from G. Okay, so this is cover and finite subcover. Fine. Now in this framework, if you are working in a system where you can talk about open sets, okay, then if all the G lambdas are open sets and G lambdas is a cover, then the collection script G is called an open cover of A. Now I want to draw your interest over here that there are plenty of systems where we can talk about open sets which are way more general than a real number system. Okay, real number system, the set of all real numbers, there is a particular example of those spaces, and those spaces, namely the topological spaces, they are way more general things than real numbers. In real numbers, we enjoy a lot of properties which are only relatable to the real numbers, only available to the real numbers. So when we want to build a theory which is outside of the real numbers, we should not assume those nice properties about real numbers. So in a topological space where there we can talk about open sets. Open sets is a much more generalized concept than the particular properties of real numbers. So there in a much general scenario we can talk about open sets, and if we have a collection of open sets which is also a cover of a set A, then that is called an open cover of the set A. Examples. Okay. First example, choose A equal to closed 1 to infinity. This set. Now Gn to be n minus 1 to n. Okay, n is running over natural numbers, so n minus 1, that is for n equal to 1, that is 0 to 1, the open interval 0 to 1. For n equal to 2, that is 1 to 2. For n equal to 3, that is 2 to 3, and so on. So this one is a open cover. This Gn is an open cover of 1 to infinity. Okay, there is a mistake. This will be n minus 1 to n plus 1. Okay, n minus 1 to n will not be an open cover. N minus 1 to n plus 1 will be an open cover. Okay, so then this one will be an open cover of the 1 to infinity, n minus 1 to n plus 1. Obviously, this is a countably infinite cover because n is running over natural numbers, so this is a countably infinite. Now, does this admit any finite subcover? This is an exercise for you. Draw figures to find out. Draw the picture, and this will be n minus 1 to n plus 1. I'll rectify this when I upload this PDF. Then draw a figure to find out whether you can choose finitely many elements from this finitely many open sets like this and cover the entire this set A, 1 to infinity. Okay. Second example. Let A be closed interval 0, 1, and let the set Gx be the open set x minus 1 by 10 to x plus 1 by 10. Okay, x is any real number from 0 to 1, and the open set G associated to the point x is x minus 1 by 10 to x plus 1 by 10. So it is, if x is 0, then it is minus 1 by 10 to plus 1 by 10. If x is 0.5, x is half, then it is minus 0.4 to 0.6, and so on. So you get the point. Gx is this set x minus 1 by 10 to x plus 1 by 10. Then the collection of all these Gx where x is varying over the closed interval 0, 1, this will be an open cover of 0, 1. Okay, draw figures, draw pictures, and you'll see how this is happening. This one will be an open cover of 0, 1. Now obviously this is an uncountably infinite cover because the index set capital lambda is the closed and bounded interval 0, 1, and this is obviously an uncountable set. So this is an uncountably infinite cover. Okay, does this admit any finite subcover? Another exercise for you. Try it. Okay. These are all easy. I mean, if you just draw pictures, then it will be very much easy for you. Okay. Almost immediately you can see whether you can find finitely many finite subcover, or you cannot find that. That will be crystal clear if you draw pictures. Okay. Next example. Let A be open interval 0, 1. Fine. Now, since this open interval 0, 1 is an open set, then for each point there in 0, 1, we find a delta x such that in delta x, the delta x neighborhood of x will be inside 0, 1, because 0, 1 is an open set, x is a point over there, so x must be an interior point. So that means there is a neighborhood of x which is entirely inside the set. So delta x neighborhood of x is entirely inside 0, 1. Fine, this happens for every point x inside the open interval 0, 1. So for every point x, define your Gx to be that interval, delta x interval around x. That is x minus delta x to x plus delta x. So this is an open set, and consider all these this kind of open sets. All these Gx where x is running over 0 to 1. 0, 1 open interval. This will be an open cover of 0, 1, of course. This is also an uncountably infinite cover, no doubt in that. Does this one admit any finite subcover? Draw figures, draw pictures. You'll understand whether this admits any finite subcover or not. Okay. All right. Now we are at a position to define to give you the general definition of a compact set. this definition of compact set is true everywhere. Wherever you want to talk about compact sets, this definition will hold true. What is the definition? A set K is called compact if every open cover of K admits a finite subcover. I repeat, a set K is called compact if every open cover of K admits a finite subcover. Alright? Okay. If you have figured out the exercises in the last set of examples, now you know that in examples first one and the third one, the open covers do not have finite subcovers for the sets 1 to infinity and the open interval 0, 1 there respectively. Okay. Hence, none of this 1 to infinity or 0, 1 is compact because every open cover must have a finite subcover. We have found a open cover there which does not have a finite subcover. So definitely these sets will be non-compact subsets of R. Fine. But in the second example, the given cover of 0, 1 admits a finite subcover. Okay. So can we conclude that 0, 1 is compact from that situation? Now look at the definition closely. It says every open cover of a compact set must admit a finite subcover. Every open cover. So as an example 2, we cannot conclude 0, 1, closed interval 0, 1 to be compact judging by the only cover given there. Okay. But at the beginning, we agreed intuitively that any closed and bounded subset of R should be compact. Any closed and bounded subset of R should be compact. So should 0, 1 closed interval, of course. Hence, the first thing, so you understand the problem. For 0, 1, for the closed interval 0, 1, we exhibit a cover, an open cover, which gives us a finite subcover. So that is very good. But the question is, will every cover generate a finite subcover? Then only we can say 0, 1 to be a compact set. So hence the first thing to do after agreeing to this sort of outlandish definition of compact set, this definition is not for real numbers, definitely. But since we have to sort of agree to this definition, sort of outlandish definition of compact set, this definition should agree with your intuition in R, right? This is the result dealt with in the celebrated Heine Borel theorem. Heine Borel theorem guarantees that if you have a closed and bounded subset of R, then that set has to be a compact set. Now let's dive into that theorem. Okay. So Heine Borel theorem, this is a closed and bounded subset of R is compact. That is, every open cover of a closed and bounded subset of R must admit a finite subcover. Okay, let's see the proof. Let K be a closed and bounded subset of real numbers. Fine. If K is not compact, then it must have an open cover which does not have a finite subcover. Okay, so let script G with same notation, script G, capital G lambda, where lambda is coming from capital lambda, be an open cover of K which does not have a finite subcover. Okay. Now, so here our argument starts. Since K is bounded, for some real numbers A and B, K must be within that closed and bounded interval A and B. Okay. Since K is bounded, K must have an infimum, K must have a supremum. So infimum is A, consider a lower bound as A and upper bound as B. So K must be within, entire K must be within the interval AB. Fine. Now consider the midpoint of this interval AB, A plus B by 2. Call it C. And consider the subintervals left part, A to C and C to B. I urge you to draw pictures over here. Okay, AB is a is a closed unbounded interval which contains k. Now we are looking at the midpoint of AB, okay, and we are looking at the left and right subintervals A to C and C to B. Fine. Now, since K, which is K intersection AB, K is a subset of AB, so K intersection AB is K. Since K is not contained in finitely many open sets from G, that is our assumption, okay, that if K is not compact, then it must have an open cover which does not have a finite subcover. So G is an open cover of K which does not have a finite subcover. So K is not contained in finitely many open sets from G. Then at least one of the portion K intersection AC or K intersection CB. So K intersection AB, entire thing is not contained in finitely many open sets. And here we are looking at the left portion K intersection AC and the right portion K intersection CB. Now both of them cannot be contained in finitely many open sets from G, because in that case, if this is contained in finitely many open sets, this is contained in finitely many open sets, together they will be contained in finitely many open sets, but we are not assuming that. So at least one of those, this left part or this right part, K intersection AC or K intersection CB, is not contained in finitely many open sets from G. Okay? Choose that subinterval, choose that portion which is not contained in finitely many open sets from G. Choose that subinterval either from the left part AC or from the right part CB whose intersection with K is not contained in finitely many open sets from G, and call that subinterval I1 as A1 B1. Okay? Fine. Now let's do this process once again. C1 be the midpoint of A1 B1, A1 plus B1 by 2. Again, as K intersection A1 B1 is not contained in finitely many sets, finitely many open sets from G, at least one of the left part of this A1 B1, K intersection A1 C1 and K intersection C1 B1 must not be contained in finitely many open sets from G. Choose the subinterval from A1 C1 and C1 B1 whose intersection with K is not contained in finitely many open sets from G, and call that second subinterval I2 as A2 B2. Okay. Now continuing thus, we get a nested sequence of closed and bounded intervals In, which is A and Bn, such that for every n, what we get? K intersection A and Bn must not be contained in finitely many open sets from G. None of them, none of K in this sequence of subintervals K intersection A and Bn, none of K intersection A and Bn is contained in finitely many open sets from G. Secondly, they are nested. In plus 1 is inside In. And the length of In is b minus a by 2 to the power n. See, for I1, the length was half of AB, that is b minus a by 2. For I2, that is half of A1 B1, that is b minus a by 2 by 2, that is b minus a by 2 square. So for nth interval, nth subinterval, the length will be b minus a by 2 to the power n. And obviously this quantity goes to 0 as n tends to infinity. Okay. Now, by my last lecture series, this is the Cantor's nested interval theorem, and the last two quantities, properties. This is by Cantor's nested interval theorem, the hypothesis of Cantor's nested interval theorem, and this says that the intersection of all these things is non-empty. There is a point xi in the intersection of all of them, right? This is guaranteed by nested interval theorem by Cantor. Now let's see what does this xi do? How does this xi behave? So fix an epsilon arbitrary. Fine. Now, since the length of the subintervals is going to 0, limit of length of in, this mod of in means length of in, b minus a by 2 to the power n, bn minus a, whatever you say. So length of in is equals to 0, then by the definition of limit of a sequence, there is some subinterval ik such that length of ik should be smaller than epsilon. This is just by the definition of limit of a sequence. This is a sequence, limit of in. The length of in is a sequence. This limit is going to 0. So for a chosen epsilon positive, we must find a subinterval ik for which the length is smaller than epsilon. Okay. Now, as xi is in ik will be inside the epsilon neighborhood of xi. Xi is inside each of i's. Xi is inside the intersection of all of them. So xi is in intersection each of i's. So xi must belong to ik. Hence, ik must be in the epsilon neighborhood of xi. Okay. Let's see the detailed picture here. So here you have xi. Here you have xi minus epsilon to xi plus epsilon. Okay, xi is stretching its hand to both left and right side, and the length of the hand is epsilon over there. Now here you have ik. Xi is inside ik, and the total length of ik is something smaller than epsilon. Total length of ik is something smaller than epsilon, and xi is inside this ik. So this entire ik has no other choice but to be inside this epsilon neighborhood of xi. There is no other choice for ik. Ik has to be within the epsilon neighborhood of xi. Correct? Okay. Let's see what does this imply. But as k intersection ik is not contained in finitely many open sets from G, this is the condition, this is the first condition, that k intersection in is not contained in finitely many open sets for every n. So k intersection ik is also not contained in finitely many open sets from G. Okay. In that case, what ik must necessarily have is an infinitely many points from k. K intersection ik is not contained in finitely many open sets from G. That means k intersection ik must have infinitely many points. If this has finitely many points, then there is no point of using infinitely many open sets from G. K intersection ik must have infinitely many points. So that means ik must necessarily have infinitely many points from k. What does that mean? Then ik, which is inside the epsilon neighborhood of xi, this implies that the epsilon neighborhood of xi also has infinitely many elements from k. What does this mean? Since epsilon is arbitrary, xi is a limit point of k. Okay. Now, what do we have? So far, we have used the property that k is only bounded. Now, we have one more property of k left. That is, k is closed as well. Since k is closed, this guarantees that xi is a limit point, so xi belongs to k. Fine? Okay. Next we see that, so as xi belongs to k, xi must also have some open set to be covered by, xi must have some open set from the family script G to be covered by, so xi must be contained in some open set G alpha from the collection capital G, script G. Okay. Now, what do we know about G alpha? G alpha is an open set. This is an open cover we are talking about. And xi is a point in G alpha. So that means xi is an interior point. So that means we find the delta positive such that the delta neighborhood of xi is inside G alpha. Okay. Now, with this delta, we repeat the exact same procedure what we did with that ik over there. But again, as limit of length of in is equal to 0 for this delta, we find a subinterval IP such that the length of IP is smaller than epsilon. By exactly same argument that by the definition of limit of a sequence, we get this. And by the same argument used earlier, this IP will also be inside the delta neighborhood of xi. Okay? Then finally what we get is K intersection IP. K intersection IP, which is definitely a subset of IP. Now IP is a subset of in the delta neighborhood of xi, and delta neighborhood of xi is a subset of G alpha. Okay, so we finally get K intersection IP, which is definitely a subset of IP. IP is a subset of delta neighborhood of xi, and this is a subset of delta is subset of G alpha. But do you see what is happening here? What this implies? This is a contradiction, because by construction K intersection IP must not be covered in finitely many open sets from G. But here we see that K intersection IP is inside one single open set G alpha from script G. This is a contradiction, as by construction K intersection IP cannot be contained in finitely many open sets from G. Hence, our assumption is not tenable, and every open cover of K must admit a finite subcover. This completes the proof of Heine Borel theorem. I'll meet you with another theorem, converse of Heine Borel, in the next video. Thank you for your patience.